Alright class, today we're going to begin looking at Unit 8, getting into our modern atomic theory. So a lot of what we're going to be doing is kind of thinking all the way back to what we covered in Unit 2 of early atomic theory, moving our way up through this increasingly complex understanding of the atom. Today we're going to do focusing on how that has changed in the past about 100 years to where we are today with our current understanding of what the atom looks like at that very small atomic scale. So yeah, if we think back to what we did in Unit 2, just a quick recap. The last thing we talked about was the Rutherford model of the atom. Again, looking at this Rutherford model, looking at Goldfull experiment that was conducted in 1909, research published in 1911. We have the big idea that we have is the discovery of our nucleus. So Rutherford was able to figure out that the atom is made out of mostly empty space, and that there's a small, very dense section of positive charge at the center of our atom. Building upon Rutherford's idea of the nucleus, James Chadwick in 1932 figured that there were two parts to it. We had the neutral neutron, as well as this positive proton that Rutherford discovered previously. So pretty much what we have is the understanding of the nucleus doesn't change much after 1932 for another 30 to 40 years. But much of this time period in the mid-1900s was devoted to studying our electrons and their movement throughout the atom. So this focus in on electrons is what gets us into this topic of modern atomic theory. When we think about how these electrons move and function within the structure of our atom, a lot of the information that we were able to figure out about our atom actually grew out of the study of light. So what we're going to do is focus this first part of Unit 8 on looking at light, and eventually we'll get into called electromagnetic radiation. But this focus on light is what's going to allow us to learn more about how our electrons are situated within our atom. So one peculiar thing about our study of light is that scientists in the 1900s figured out this thing that we call a wave-particle duality of light, and that light can behave as both a particle and as a wave. So it can be like the small, circular almost object that moves through space, or it can be something like a wave, either a sound wave or wave in the ocean. It can behave like that wave traveling through. So before we get into looking at a little bit deeper information about this, just a few terms in what we're referring to by light. Typically what we think of as light in our day-to-day lives is looking at what we think about this visible light. Although this is really only one part of this electromagnetic radiation we're going to focus in on from here on out. So all electromagnetic radiation is a type of energy. So these energy waves are made up of electric and magnetic fields, and many of the things that we associate with are things that we actually use in our daily life that we have heard of before. So while visible light is the most commonly used term, most common thing we think about when we refer to light, we also have to include in this new definition of our electromagnetic radiation things such as radio waves, microwaves, infrared waves, ultraviolet waves or UV rays, X-rays, and gamma rays. So all of these various different types of waves are all things that are going to be light, are going to be pieces of our electromagnetic radiation. So when we think about light as a wave, again, only one of its two forms of appearing in the universe. Just a couple of key terms we want to cover before we get into a deeper study of this type of wave. But the first thing we have is our amplitude is measuring the height from this kind of 0 point of our wave up into the top of our crust here. We're going from this 0 point of our x-axis, going up to the top of our wave, that's going to be our crest. This is going to tell us the intensity of our light. but it's going to be something that we're not going to focus too much on throughout this unit. The big piece of information that we get from this wave of light is looking at the wavelength, or the distance between two of our crests here. So in a way, right, our wavelength is telling us the length of our wave, and we represent this wavelength in our formula we're going to look at in just a second here by the Greek letter lambda. This Greek letter is going to be what's going to be used as the variable for our wavelength. And yet, because we're dealing with a distance, a length, our SI unit of length is always going to be a meter. If they give us a wavelength in terms of centimeters or nanometers, we're going to want to convert back into meters using those SI conversions we looked at the beginning of the year. When you think about light, all light, whether it's a radio wave, whether it's visible light, whether it's a UV wave, all light is going to travel at 3 times 10 to the 8th meters per second. That is going to be in a vacuum. Something you'll see next year in physics is that depending upon the medium we travel through, whether we're in a vacuum, whether this is light going through water, whether it's going through some other object, that speed of light's going to change. But for what we're doing right now is we're going to pretend, think about this ideal situation where light is only traveling through a vacuum. The equation we're going to derive in just a second is going to represent the speed of light, this 3 times 10 to the 8th meters per second, as a variable c. Again, this idea that all light travels at the exact same speed, this 3 times 10 to the positive 8 meters per second. This is actually going to be one of Albert Einstein's greatest contributions to science. Another way of thinking about waves is not necessarily the distance between our two peaks or two crests, but we can also think of the frequency of the wave, which is a measure of how many cycles pass by a given point in a given amount of time. So one way to think about the frequency of a wave is think if you're standing at the beach and let's say you took out a stopwatch, hit start, all you're doing is counting up the number of waves that crash along the surface. Right, so think at that given point along the beach, how many waves pass through, how many cycles pass through. That would be like the same idea of counting how many waves crash on the beach's surface within a minute, or within an hour, or whatever unit of time you want to use. We're going to be using the letter F to be the variable we use for our frequency, and this SI unit referred to as cycles per second. What this means is that it's going to be 1 over second. Some books will also write 1 over second as equal to second to the minus 1. Sorry. This negative exponent means we divide by 1 over s. But we're going to use most of the time in this class, we're going to be looking at the unit of our hertz. So hertz is going to be abbreviated Hz. So if we think back to some of the kind of key terms we saw in this last couple slides here. First was, he said c was our speed of light. It would be 3.0 times 10 to the 8th meters per second. Our wavelength, lambda, again, it is going to have the units of meters, and our frequency, f, is going to have the units of 1 over s. And just going back to the top there, that 3 times 10 to the 8th meters per second is what we're going to refer to as our speed of light. So if you look at the units we have here, meters per second, meters, and 1 over seconds, we can actually create a relationship between these three variables. And we're going to say is that our speed of light is going to be equal to our wavelength times our frequency. So we have, again, our speed of light. It is always going to be this value up at the top here, this 3 times 10 to the 8th meters per second. Our lambda signifies our wavelength. And our f is going to be for our frequency. So our wavelength and frequency are going to be two values associated with a given wave. In this case, we're dealing with waves of energy, these waves of light. So electromagnetic radiation is going to be described by this equation we have here. Again, when we think about our units, C is going to be meters per second. Our wavelength is going to be meters. Our frequency is going to be 1 over second, or our hertz. So if we multiply meters by 1 over second, we're going to get the meters per second that we see on our left side. That says velocity, the speed of light. So let's say we're looking at a particular wave of light that has a frequency of 1.5 times 10 to the 15th hertz. Where our job is to figure out what is going to be the wavelength of this light. So first thing we're going to write down is we know our frequency is going to be this 1.5 times 10 to the 15th hertz. And all we're going to do is we're trying to solve for our frequency, we're going to solve for our wavelength. This is going to be our unknown value here. So this speed of light, it's always going to be a constant. It's always going to be that 3 times 10 to the 8th. So if we apply our equation here, we have C is equal to lambda times F, wavelength times frequency. We're going to have 3.0 times 10 to the 8th. It's going to be equal to our wavelength times this frequency of 1.5 times 10 to the 15th hertz. So all we have to do is isolate our variable lambda. You can do that by dividing both sides by 1.5 times 10 to the 15th. What we can do is we can solve for our lambda is going to be equal to 2.0 times 10 to the negative 7th meters. So again, all we're doing is applying that equation of C is equal to lambda F to figure out what our wavelength is. So one quick note, if we go back to our equation here in terms of our wavelength and our frequency, we multiply those together, we get our speed of light. Because our speed of light is always going to be a constant, what we can say is that any time our wavelength increases, what that means is that our frequency has to decrease. So we have a large wavelength, means we're going to have a small frequency. We can also look at the flip of that. Let's say our wavelength decreases. The end result is going to have a large frequency. So again, because these two are lambda and our F, we're going to say that they are inversely proportional to each other. Again, if one of them increases, the other has to decrease. So in addition to talking just about the speed of our light, our wavelength, and frequency, another thing we can think about is the energy of this light. So we're going to say our energy of light is going to be inversely proportional to our wavelength, but we're going to be directly proportional to our frequency. And in setting up this proportion, what's going to allow us to go from a proportion into an actual equation is going to be this thing we call Planck's constant. It's going to be represented by an h. The variable h is going to be used in our equations here. But it's going to be this constant that's able to help us relate our energy of a photon. So again, here, instead of dealing with light as a wave, we're going to be dealing with light as a particle. The one kind of tricky thing with light here is we're going to be flipping back and forth between whether or not we look at light as a particle versus as a wave. But this Planck's constant was derived from the energy of a photon being compared to the frequency of that photon. And Planck's constant is going to be equal to 6.63 times 10 to the negative 34th joules times second. So the first thing we were able to get from that top bullet point was we know that our energy is going to be directly proportional to our frequency. So we have directly proportional to frequency. This little fish looking sign here just shows that we're going to be proportional. So energy is proportional to frequency. This other point here that says the energy of light is inversely proportional to wavelength. Anytime we have something that is inversely proportional, what that's going to look like is energy is going to be proportional to 1 over our lambda. So 1 over our wavelength. Now to go from this statement of proportionality into an actual equation, we have to make use of this Planck's constant. So we said Planck's constant was a proportionality constant that relates energy of a photon to its frequency. So that means is if we take the energy of a photon, it is going to be equal to Planck's constant times our frequency. So we have our energy of our light. Anytime we're dealing with energy, it's going to be in terms of joules. And we have our h is going to be Planck's constant. Yeah, we have it as at 6.63 times 10 to the negative 34th. This unit is going to be joules times seconds. We have is for our frequency. Again, we can either use 1 over seconds or we can say hertz. They're both the exact same unit. So now we have one equation describing energy in terms of Planck's constant and frequency. We can also create an equation for energy that's going to be in terms of our wavelength. So if we go back to that equation for the speed of light we saw earlier, that c is equal to lambda f, what we can do is we can solve this equation for f. So if we divide both sides by lambda, what we get is our frequency is equal to our speed of light divided by our lambda. This can now get plugged in, substituted into our equation for f here. So one way of writing this energy equation is energy is equal to hf. The other way we can do this is by replacing our f with speed of light divided by lambda. So all we've done is plugged in the right side of this equal sign here in for f. And we can say that energy is equal to hc over lambda. Now the only difference we're looking at here is now c again is that speed of light. And our lambda is our wavelength. Alright, so we'll do one example question here before we end class today. So when we look at all these various types of light along this electromagnetic radiation, they're all going to have their own wavelengths and their own frequencies. So for instance, if we look at the section of visible light, all of our colors along the rainbow are Roy G. Biv. They're all going to be representing particular wavelengths of light. So let's say we're trying to figure out what the energy is of red light. Red light, we can look up on a table or online here, is that the wavelength is going to be 750 nanometers. If we think back to our SI unit conversions, we can look up that 1 nanometer is equal to 10 to the negative 9th meters. Right, so these are two bits of information that's going to help us figure out what is going to be the energy of our red light. So first thing we can say is that our wavelength is going to be equal to 750 nanometers. This is the same thing as 750 times 10 to the negative 9th meters. Yeah, we know if 1 nanometer is 10 to the negative 9, instead of having 1 nanometer, we have 750 of them. All we have to do is multiply 750 by 10 to the negative 9th to get our wavelength in terms of meters. Again, meters is going to be our SI unit for wavelength. So we always want to convert into meters anytime we're given this distance here. If we're thinking about what our energy is, because this question gives us a value in terms of our wavelength, it's much easier to use our second equation that we've derived up here. Our energy is equal to hc over lambda. So energy is equal to hc divided by lambda. We can say energy is equal to Planck's constant. So again, back up here, we had Planck's constant of 6.63 times 10 to the negative 34. We're going to multiply that by c, our speed of light, which in the vacuum is always 3.0 times 10 to the 8th. And we divide by the quantity 750 times 10 to the negative 9, because that's going to be what our wavelength is in terms of meters. So when we do this multiplication division, we are going to get a final result of our energy is going to be 2.65 times 10 to the negative 19 joules. Again, energy, SI unit is always going to be joules. So what we have is this is going to be the energy of a single photon of red light.